For solving of dynamical systems, sometimes is useful to use so-called Cartesian coordinate system. Generally, it is three-dimensional system where we have three axes x, y, z, and these axes are perpendicular to each other. So I can denote here base vectors I, j, k, and position of a particle in this coordinate system we define by x, y, and z coordinate. So it's for position definition. And the definition of other kinematical quantities is regarding velocity. It is that x dot, what is yx, is dx over dt, y dot, what is vy, is dy over dt, and z with dot is vz, what is equal dz over dt. And acceleration, it's a second order of derivative, so it is x with two dots is ax, it is vx with dot, so it is dvx over dt, and it is second derivative of x with respect to time. Acceleration in y-axis is y with two dots, it is equal ay, and we can use this this expression. And z with two dots is az, acceleration in z-axis, and it is second derivative of displacement z. If we solve a motion, so we can consider there acts some force to this particle. So we can define force by its components. So this is fx, fy, and fz. So we define acting force F by components fx, fy, fz. We can also denote a positive orientation of acceleration. So in this direction we measure positively oriented acceleration in x component. This is a y and a z. And if we draw free body diagram, and if we use D'Alembert's approach, so then in accordance with definition, that d is equal minus ma, and then if we consider that acceleration a has three components, ax, in, ay, az, so we can define d by components, dx, dy, dz, similarly as acting force. But according to definition, these components has opposite direction than positively oriented acceleration. So against positively oriented acceleration I draw components of D'Alembert force. Then we can write an equation of force equilibrium. So generally we can write that sum of all forces over all I plus D is equal to 0, and this is vector equation, general vector equation of dynamic equilibrium. So it's a vector equation of dynamic equilibrium. And if we work with three-dimensional space, we split this equation into three component equations. So component equations are 1, 2, 3 for direction x, y, and z. So we can write that sum of all forces in x direction minus dx, because it's this direction minus this direction, is equal to 0. Analogically, the same for y-axis, minus dy is equal to 0, and finally fiz minus dz is equal to 0. We can add force specification. In this case it is only about D'Alembert's force, because dx is m by ax, dy is m by ay, and dz is m by az.